undefined.
Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever, and we're continuing our exploration of binary operations. Today, we are going to talk about the inverse. Yes, that's right, the inverse, and it shall not be unwritten. We'll check back in with Miss Bettingfield in just a moment. Let's get started, shall we? So, for the inverse, let us consider a binary operation star on a set S, so we're familiar with that, with an identity element E, which is an element of the set S. So remember, we talked about identity element before, and to go back to multiplication, the identity element for multiplication and the real numbers is 1, because anything multiplied by 1 is that anything. And for addition, it is 0, because any number added to 0 is that number. The identity of the number does not change after the operation, hence the word identity. Okay, so that's just a quick little verbal review of that. So back to inverse. For A, which is an element of S, so that is any element within the set S. Okay, an inverse element, A to the negative 1, is an element of the set S, exists for A if and only if A to the negative 1 star A is equal to A star A negative 1, which is equal to the identity element. Don't get freaked out by A to the negative 1. That is just the notation for the inverse. That's all. It's just the notation for the inverse. And this is really very, very simple. With all these equal signs, it may look a little bit complicated, but all we're saying is if you take the inverse, multiply, or not multiply, sorry, and you perform the binary operation on the element, and then you use the commutative property and do the same thing, the element, and you perform the binary operation on its inverse, that has to be equal to the identity element. Now, we don't do all this at one time. We would first take the inverse and the binary operation of the element and see if it's equal to the identity, and then the same must be true. This is simply just the commutative property, which you're familiar with. Okay, so what do we got hidden under here? For addition in the real numbers, each element has inverse negative A. Okay, since A plus negative A is equal to negative A plus A equals 0, where 0 is the additive identity. So we already talked about 0 being the identity element for addition. And this is really just to get you familiar with what an inverse is. You know, think of a real number like 3. Well, if I take 3 and then add negative 3, I get 0. And the same if I use the commutative property, I would still get 0. So that's why every element in A has an inverse. Okay, that's an important distinction too. We'll get to that in a second. No inverse exists for the positive integers for any element in the positive integers. And that makes sense because we're only combining positive integers. So we can't get 0 when we have the with addition. For multiplication, for A, an element of the real number subtract 0, it has inverse 1 over A. Since when we multiply that, we get 1. Which is the multiplicative identity. Okay, so you see how we take the element and then we multiply its inverse and we get the identity element for that set. That's all that we're going to be doing with binary operations. 0 is a unique element in the real system which does not have a multiplicative inverse, and that's only because we can't have 0 in the denominator of a fraction. That would indicate division by 0, which we all know is impossible. So here's another theorem. If a binary operation star, if we let that be an associative binary operation, so we know it's associative on a set S, and it has an identity element E. If an element A, which is a part of S, has an inverse, then it is unique. It's the only one. And that applies if the operation is associative. And maybe it's better to think about the contrapositive. If the inverse of an element is not unique, then you don't have associativity. So that's another way to disprove associativity. The proof to this theorem right here, the contrapositive of the theorem. I'm sorry, this is the proof of theorem 4. I apologize. If you want to pause and take a look at this, you can, but I'm not going to spend time on the video or in the video to talk about it. We can talk about it in class. Okay, so let's get to an example. Consider the binary operation star on the real numbers defined by A star B equals 3AB. This might be familiar. We did this, I believe, for the identity. Yeah, we did. This was one of the examples we did for the identity element. Determine the values of A, which are an element of the real number system for which star has an inverse, and the value of the inverse in each case. Okay, so we're just looking for an inverse here. And for which elements it's true. It does not necessarily have to be true for all elements of the real numbers. So we're finding which values in the real number system have an inverse. They don't all have to. So we're just trying to figure out which ones. And here is just the definition, so we have something to get to go by here. We first have to find the identity element. Now, if you recall, the identity element for A star B is equal to 3AB is 1/3. And let's just do that real quick, because the identity element here, we look for it this way. We say assume B is the identity element. Okay, and if that's true, then A star B has to be equal to A. Okay, so let's figure that out. So if A star B is equal to A, and remember A star B is defined as 3AB, then 3AB is equal to A. And subtracting A from both sides, 3AB minus A would equal 0. So let's see, what can we factor out here? We can say A times 3B minus 1 equals 0. And remember, we're only interested in B because that's what we have said is the identity element. So I'll just set 3B minus 1 equal to 0. 3B equals 1. And B is equal to 1/3. So we do have an identity element. So that's what we're going to work with here. So I'll do this part in blue here to answer this question. Determine the values of A for which star has an inverse. So here we go. I'm going to say if A has inverse B, then, and I'm just taking this right from here, well, instead of A negative 1, just to make it easier to work with algebraically, I'm going to use B. So I'm going to replace A negative 1 with B here. Then B star A has to be equal to A star B. And again, I'm replacing A negative 1 with B. Has to be equal to the identity element E, which we have defined right here, or have not defined, have found as 1/3. Okay, so let's get this party started. I will write again that A star B is equal to 3AB. Okay, So we'll start with B star A. Okay. So B star A has to be equal to 1/3. Okay. Well, B star A by this definition would be 3BA has to be equal to 1/3. And so if we solve for B, we would divide both sides by 3A. So B would equal 1/3 divided by 3A, which gives us, let's see, that would be 1/9A. Okay. And so now we'll do, so we found that, okay, and A star B has to be the same thing. So we're hoping that we get 1/9A. So A star B has to be equal to 1/3. And again, A star B is defined as 3AB. So 3AB equals 1/3. Looks like it's going to work out well, but I'll work it out step by step for you. Dividing both sides by 3A. So B equals 1/3 over 3A. And that gives me B equals 1/9A. So we got the same thing. So we do have some inverses that exist. Now what we do have to state here, and I should have stated it before, is A cannot equal to 0. A cannot be equal to 0, because then we would have 0 in the denominator, which is undefined. And so we can conclude that, and I'll do that up here, that each element A, sorry about the how this is kind of going vertically, an element of the set real numbers, not including 0 there, has the inverse 1/9A. That is our inverse. Each element A has inverse 1/9A. And then we would need to state and element 0 has no inverse. So this is very formal here. If I were to ask you, find the inverse elements for all of A, or if they exist, what are they? You would just have to say 1/9A is the inverse element, and that 0 has no inverse. It's the only exception. Okay, hope you enjoyed that. I certainly did. Be sure to get started on your assignment, and I am going to go out with Natasha, and hope you enjoy it. So, with that, I am